This time I forgot to mute people, so some of them are already talking.
Yeah.
Hello, everyone. Ahmed Saroush here. We are going to give it another 3 to 5 minutes to have all participants, and we'll start the talk afterward.
Yes. Hi, how are you doing? How was the conference, the government conference?
May I ask everyone to mute their microphones and shut down the cameras, please?
Yes.
Dr. Aziz, if there was a technical problem with me, Salah from our team is actually in the meeting and will continue supporting you. So,
Okay.
so I forgot to tell you that we at the end of the session we let people to raise hand and directly ask their question from you. So,
Okay. Sounds good.
we have 21 people so far. We give it another minute and then we'll start the session.
Sounds great.
Okay, I think we can go ahead and start. Hello, everyone. Welcome to the 11th talk from Petrolern at Home seminar series. I'm Hamid Saroush, CEO of Petrolern LLC, and today I'm pleased to introduce our expert speaker, Dr. Aziz Khlaifat. As you know, we are all experiencing a very difficult time with both COVID-19 and low oil price. So we are very blessed at Petrolern to be able to feel part of your time during this difficult time with some hopefully technical, useful technical knowledge. So as you know, the objective of this seminar is basically to keep you learning and motivated during this depressing time. So specifically, one of our plans is to provide talks on topics outside oil and gas, such as geothermal energy, carbon storage, and subsurface energy storage to hopefully open doors to, to new opportunities for those people who are who have lost their jobs or are in risk of losing their jobs. So I hope that we all pass through this time safely and in good health. I would like to express my sincere gratitude again to all industry experts who accepted to give the talks. The good news is that our schedule for June is completed now, and it will be posted on LinkedIn very soon. We have very good actually and interesting topics from different industry leaders, again on geothermal, on oil and gas, and carbon storage. So in case you are interested to give a talk, now we just starting the schedule for July. We have still 4 more talks scheduled for May. Please make sure you follow us on LinkedIn for updates about the upcoming P.A.S.S talks. Also, we are announcing a few job positions in the next few weeks. So just stay tuned and check our website for those job openings. Our next seminar, for your information, is going to be on Friday, May 18th, a geothermal talk by Ida Kerknell from the lovely Copenhagen, titled Modeling of Scale and Corrosion Potential in Geothermal Wells, Plants, and Oil Producers. So before introducing my best friend, Dr. Khlaifat, I would like to ask everyone to mute their microphones and turn off cameras for best quality. If you have any questions, please raise your hand at the end of the session, and we let you ask your question directly from Dr. Khlaifat, and he will be kindly answering as many questions as possible. If for any reason you could not actually stay with us until the end of the meeting, so we are recording all the talks, and we'll share them on our website at www.petrolern.com. So Dr. Abdulaziz Khlaifat is a professor of petroleum engineering at the American University in Cairo. He has more than 23 years of academic and industrial experience in chemical and petroleum engineering. Prior to AUC, Dr. Aziz was a professor of energy engineering at the American University of Iraq in Suleimania, founding head of petroleum engineering at Abu Dhabi Polytechnics, and professor and director of Prince Faisal Center for Dead Sea at Muta University in Jordan. He also worked in the industry as a senior reservoir engineer and a manager for Weatherford in Dubai and Dhahran, Saudi. He has been co-founder of different academic departments, research centers, and a business incubator. Dr. Khlaifat has authored more than 90 publications in the areas of flow-through porous media, hydrocarbon reservoir engineering, unconventional tight and shale gas, managed pressure drilling, catalysis, two-phase flow modeling and simulation, and Dead Sea related research. He's a recipient of several technical and academic awards, and was listed among the notable alumni on 2017 by Worldwide Association of Notable Alumni. Dr. Khlaifat obtained his PhD in chemical engineering, reservoir engineering in 1998 from Illinois Institute of Technology in Chicago. Apart from all this qualification, Dr. Khlaifat is one of the best in preparation of shisha. So if you have any question with that respect, you can ask him. So his title is Shale Gas, No Go scenarios. So with that said, I want to pass it to Dr. Khlaifat to start the talk. We're all waiting to hear that talk.
Thank you so much, Hamid, and thanks to Petrolern for having me today. And thank you guys for being with us. I know it's Friday and everyone has the spirit of weekend. Nevertheless, you decided to join us. I will try to make my presentation as light as possible, but in case if it will not be, you can stop me and let me know that. So, as you know, the journey of shale gas is unconventional compared to other fossil fuel resources. So what I'm going to start with is a background. I will shed some light on shale gas background, and then we will talk about drilling, completion, and stimulation of shale gas. After that, we will visit resource evaluation, and then we will have a little bit of production, okay, and flow back, and we will wrap up our presentation by environmental issues. And you know, whenever we talk about fracking, so environmentalists basically oppose what we do with respect to shale gas. Now, does it really worth it to go for shale gas nowadays? If you look at gas prices, as per EIA projection or assumption for gas prices by the year 2050, it seems that the largest or the maximum dollars for which gas can be sold is about $6. And this is, of course, if we have a low oil and gas supply. So in case if the supply will go down, then the cost will go up. And $6, this is the maximum that they can reach. If you look at nowadays or today's price is 1.71. Even today's price is actually less than the assumption made by EIA. It should be about $3, but the price is less. Does this drive us away from shale gas? Of course not, because shale gas is, or the gas obtained from shale is environmental friendly compared to methane, compared to coal. So when it comes actually to energy needs projected until the year 3000, where we will be not here, so eventually the main contributor nowadays is crude oil and gas. But in the future, we see a paradigm shift actually in contribution. So coal will has its play, although some countries like United States, as a matter of fact, or as I know, now they have 0 plant operated on coal. So some countries are getting away from coal. Nuclear energy is actually booming in some countries. If you look at the Middle East, so United Arab Emirates now going to have a plant by maybe the end of the year, first reactor will be operated. And some countries like Germany, USA actually are getting rid of this source. Renewable energy is a new player, okay? And it has more share. So if you look at basically the right, what we're gonna have, more energy will come from renewable sources compared to fossil fuel. Well, if we go back to oil prices in 2008, when it rocketed the sky, $148. That one was a killer to oil industry in terms of sale. Because many non-producing countries started looking for new sources of energy or energy mix, where actually advancement in technology went through, and it became much more feasible to invest in new technology or in renewable energy rather than oil. Now, when it comes to shale gas share in the United States, it's clear from this figure that by the year 2035, shale gas will contribute almost 50% to US dry gas production, which means shale gas is targeted by United States. In addition to that, other countries actually invest in this business a lot. Some countries started and the projects were halted, and some countries basically are planning to do so. Some countries under exploration. In some countries, shale gas development actually was banned, okay, like what had happened in Bulgaria and in France because of environmental issues like hydrofracking. And some countries are producing from shale gas like United States, Canada, China, and Argentina. So basically, now we have almost 4 countries producing, and the rest are either under exploration or the process was halted. Now, when it comes to resources, what can we see here? We see actually China became actually a competitor to United States in terms of resources, while some other countries like Australia, Algeria, they have lots of resources, and we did work actually in a project in Algeria to develop shale gas reservoir, but it seems the project was halted and they did not start the drilling yet. Okay. Well, what are the critical drivers to this type of industry? You or most of you know that this shale gas actually development did boom because of 2 reasons: horizontal drilling and multi-stage fracking. Okay, so advancement in technology is expected to contribute to extra production from shale gas. And by the year 2025, as per National Petroleum Council, so they expect the contribution to be 4 PCF, which is a large number. But after 2025 and in the future, eventually there will be no hanging fruits with respect to shale gas. So shale gas will be harder to find, will be deeper, will be hotter, will be more remote, okay, where it will be costly and high T and high P as well. So eventually there will be a need for further R&D to target those shale plays. Now, with respect to a spectrum of shale gas, okay, is it coal or tight gas? Actually, the spectrum of shale gas varies between coal and tight gas. We all know that in tight gas, we have gas stored by compression or 100% compression in secondary porosity, while in core, we have gas stored by adsorption, okay? So 100% actually stored by absorption. And the spectrum between these 2 sources eventually is allocated or saved for shale gas. So shale gas could behave as a tight gas and it could behave as a coal. So in here, we talk about 2 types of gases. The one which is a free gas when we get closer to tight gas. The other one which is adsorbed gas when we get closer to coal in terms of properties. It's so challenging to address such a resource, and the challenges eventually span the life cycle of shale gas well, starting from drilling, okay? The cost of drilling of shale gas is high, and usually operators think of one thing: how can they reduce the price, okay? Manage, okay, the differences between gas and oil is another issue. How can they geosteer to target hotspot while they drill? Okay, this is another issue and a question actually raised usually. And to build suctions and lateral more quickly, okay, so to increase rate of penetrations. So with respect to evaluations, okay, it's so important where to place the well, because we don't talk about anticline, we talk about horizontal, lateral. Okay, which part is the best to place the well? Let's say if it is exploration well, imagine placing an exploration well in a place where we have minimum amount of gas. So basically, this gonna be costly and useless. Is it for shale gas? It is required to integrate multiple data sets, whether they come from core analysis or they come from logging. Okay, and high quality actually logs are required. Okay, for further development of such gas, and of course, determination of sweet spot is another issue during evaluation. Now, during completions, it's geomechanics actually plays significant role in here to find fracture conductivity and to decide for whether to go for multi-stage, how many stages have to be carried out, whether the well has to be completed in an open hole or closed hole or closed cased hole, okay? And when it comes to frac fluid, actually a decision has to be made about that one and its content and whether to use slick water for viscosity purposes. Now, with respect to production, we have lots of water to get rid of, okay? And we need to deal with the frac flowback, okay? And to handle this quite good. And of course, to meet environmental demands. And again, we need to clean up our well in order to have excellent well testing afterward. Now, intervention, we know that production from unconventional and especially shale gas declines by almost 70% during the first year. So we have to intervene almost every year or every other year. So we have to refrac in order to restore production and to do this every other time when the production declines or goes down. Now, what I had shown are the challenges actually presented usually by operators. When it comes to surface companies who drill and put those wells in production, they come up with different scenarios actually to address each of the challenges. As shown in here, I am not going to go over them. The list in here might vary from a surface company to another, and definitely they can add more components. And as more components show up, eventually the cost of drilling and completion goes up. Now, if we go back to operators, operators need the project to be fast, okay, and not to go through infinity loops, and they need it to go through a prediction, pilot, and production. And they prefer operators to have prediction based on the data they have from other wells, okay, close to the proposed, let's say, shale gas play, and to make a decision whether to go for a pilot or not. And of course, sometimes cost plays significant role whether to go or not. And in the pilot, usually they drill vertical wells, okay? And the issue related to shale gas pilot project, it's not a single well project. So we have to have multi-wells, and then we move basically the process to development where we go laterally and we drill horizontal well. Now, evaluation continues, although during horizontal drilling and completion and stimulation is a big issue when it comes to horizontal wells. Surface companies, they come up with loops, okay, for eventually to address the process in here. They still talk about prediction and pilot as a one phase, okay, and they move it to production, and they do some basin study or screening based on the old log core cutting analysis, whatever available actually in the archive of operators, okay. Now they move directly to after exploration and after drilling a vertical exploration well. If there are prospects, eventually they move to a horizontal well to produce. And more or less, surface companies think of carrying out almost the same analysis, the one shown actually at left in here, okay? With some of the analysis have to be repeated for some key wells, okay, not for all wells. So they can exclude or minimize the number of wells for the sake of actually saving money for operators. Now, from horizontal wells or horizontal production well, we get some data, okay? And we feed these data back to reservoir evaluation, and we update as the process goes on. So in here, there are two gates actually to pass through. The first one going from vertical exploration to horizontal production. And the second one is the field development plan, which means the process is continuous as a function of time, where we have to update our models and to update our plan for the sake of higher production. There is no need to reinvent the wheel. Countries rely a lot actually in USA practice, okay, or what had been done in United States with respect to shale gas. And they can benchmark their shale play actually with United States shale plays or shale basins, okay? And based on that, they can take initial decision whether to go or not to go. And what's important actually when it comes to shale gas development, it's important to know the area of the basin, okay? And thickness, how thick it is. If you look at the thickness in here, if you look at Antrim, actually it's so thin, 12 to 70 feet. And New Albany is 50 to 100 feet. TOC is an important factor to look at in here. So TOC should be greater than 1%, okay, in order to go. Porosity, this is tight formation. Porosity is less than 10%. Even in Barnett, in here is 4 to 5%, which is, we talk about a brick, very tight rock. Gas contents varies, okay, from a basin to another. It was determined actually as per the screening and based on different sources. If the gas content is more than 50 CSF per ton, this could be a good basin to drill in. Original gas in place or gas in place. So this has to be estimated, and we will see how can we evaluate this one. Now, based on those factors, so we go back to USA basins, and we can summarize what we need to look at in order to take a decision to go. So the first thing, area thickness and gas contents. So area should be greater than 200 square miles, 50 feet thickness as a minimum, and 40 SCF per ton gas content. Then we talk about total organic carbon of 1% or larger. ABI is 150. This is for dry gas. Then thermal maturity. So the reservoir has to be mature. And when we talk about thermal maturity in here, we refer to vitrinate reflectance, and it should be greater than 1 in order not to drill in oil window. Other studies, again, mechanical properties of the reservoir have to be known, and to know whether we have natural fracture, and to know more info about frackability in the future and drilling. So geomechanics, again, has to be done. Geochemistry, geology, lots of studies have to be done for such a reservoir. So if we put it in terms of flow diagram, so we check these three things, TOC, shale thickness, and gas contents. If they are low, okay, compared to the figures shown in the previous slide, then we have to take a decision. This means that the shale play is unproductive and we stop. We have the first no-go here, okay? But if these actually parameters in here are high, which means the shale is rich actually with organic matter, then we look at thermal maturity, and we have 3 values for thermal maturity as shown. So if it is less than or equal to 0.5, the shale actually considered to be thermally immature. And in this case, again, we have the second no-go. So it's better to stop or not to go further. So if RO is between 0.6 and 1.1, So then we can drill in oil or condensate window. And if we keep doing so, we can produce gas or oil or condensate or oil. Now we care about the dry gas, so RO has to be greater than 1.2 or greater than 1. So we safely can proceed, and we can know that this is a good go for the process. The next actually topic is related to drilling, completion, and stimulation. So again, in here, we need to know whether this is a new shale play, okay, or drilled previously. If it is a new one, we have to go for vertical exploration well, and we have to make a full flange evaluation for this well. If it is actually not new, again, we have to make some assessment or evaluation, but not full flange evaluation. After that, we decide whether a horizontal well completion is feasible, how large the reservoir is, okay, and we check whether we go for horizontal or we keep going with vertical, and we complete the well with an open or a case. So lots of things done actually similar to conventional gas. Now, horizontal versus vertical wells, when it comes to production, you all know that it's always better to go for horizontal, because it provides more drainage area and interaction actually with the reservoir. Environmental footprint actually is less damage to environment, and it was determined that having 6 wells drilled from only 1 well pad results or replace 16 actually vertical wells. And what's shown at left here, production for Barnett Shale actually for 2 different years is coming mainly from a horizontal well, where production from vertical well diminishes, okay, or it goes to a very low number. Now, how to drill shale gas? We know that the reservoir has very low pressure. Is it good to drill it under balance or to keep going and drill conventionally over balance? It was proposed actually, and by some companies, and there are some studies that showed under balance drilling resulted in significant values when it comes to production. Also, it's so good to drill under balance in order to avoid damaging the delicate shale gas formation. And I say delicate, it's so hard rock, okay? But delicate in terms of damage. It can be damaged quite easily. And the other thing, production could be increased significantly if shale gas can be drilled under balance, and the net present value eventually can be increased by under balance. This was confirmed actually by British Petroleum study, where they found out, as shown in here, if the shale is drilled under balance, then production can be increased almost by 500 to 600%, okay? So, and this is really excellent case history, okay, by British Petroleum about different types of rock, where shale is included among the rock. Now, when it comes to cost, actually, cost of drilling is almost equal to cost of completion, as shown in this slide. If you look at left in here, so the cost is almost 50% for drilling and 50% for completion. Nevertheless, the cost for the next year, or 2011, Eagle Ford, actually Shale Basin, the cost is more for completion, which is 60% compared to 40%. And this is driven by having longer lateral, which is 5,000 feet, and having more frac stages. It's actually having 20 stages compared to 2010 stages, which is 14. The other thing that you need to point attention to in here is frac stimulation cost. So frac stimulation is 35%, while in here frac stimulation is 45%. So the main cost eventually comes from fracking, okay? So fracking is so expensive, and imagine doing this job every year or every other year to restore production. Now, not every shale gas basin is a good candidate for fracking, okay? Geomechanics again has to show up, and we need to know the composition of our rock, okay? Or elemental analysis of our rock has to be carried out, and to find whether the rock is brittle or ductile, okay? And it was determined that out actually if we cross-plot Young modulus versus Poisson ratio, the area above the green line in here, okay, any value selected in the green line could result in having a good brittleness of the rock, where if that rock or shale rock is fracked, it will shatter. On the other hand, if we go below the green curve, the rock will be ductile, and we need to have, or it will resist actually fracking, and the fracking job will create nothing but a planar fracture in the rock. The other thing that have to be tested is clay content, and it was suggested that if clay content is more than 50%, it's no-go scenario. So clay content is a big issue in here because of swelling and clay behavior in the rock. So 50% or more, it's better not to frack, and this is another issue because there is no way to produce shale gas unless you frack, or to produce or to reach good production level unless frack. And this means no go, we have to stop it here. Number of frac stages, again, they play significant role in increasing production, and it was clear lately that number of frac stages was increased, but of course this has to be associated with amount of gas, okay, distributed in the reservoir, as we're gonna see later, and the hot spots actually in the reservoir to target. Preliminary study has to be done in order to decide the number of stages, and it was determined that increasing the number of stages increases economics for the same well. Well, going back to the challenges, guys. So in here, we have challenges associated with the reservoir quality. And it's a bit different when we talk about shale gas. We need to know the gas in place volume, and we have to start this process right from retrieving the core. And we need to know the permeability to gas. Permeability is so low, as we've seen, the porosity is low. Permeability is in the range of 900 Cs, okay? And we need to know frackability or rock mechanical properties. The other challenge is reserves quantifications or estimations, okay? In here, logs don't provide full answers, and we have to have whole core from day one in the exploration one. I mean, when we hit the reservoir, and core analysis has to be carried out, and then cross-plotted versus or integrated with the log, okay? We mentioned this one when it comes to reserves. We have a decline of 70%. We need to produce in order to know our reservoir. So it's, but this is not a case if we compare it to conventional reservoir, where we rely actually on decline curve analysis and material balance for reserve estimation. So this is a bit tedious in this case. High exploration and development costs. We see in this one actually with respect to drilling and completion, we talk about 50-50. Now development, if we have, let's say, many wells drilled from one pad, okay, so we could save, but if we have to use multi-pad, eventually the cost will go up. Environmental issues, this is we will visit by the end of the talk. Now, when it comes to evaluation, if it was determined that the shale play is basically good and it can be developed, okay, so we check where the gas is first stored, okay, is it free gas or adsorbed gas? So if it is free gas, or we have lots of free gas, and this, as a matter of fact, we don't know this. So we have, anyway, we have to start the process of evaluating free gas in the shale, starting from the first minute or first hour or the shorter time as we retrieve the core to the surface. And the device used for this purpose is called canister, and the analysis called canister analysis. Now, with respect to adsorbed gas percentage, and you've seen it in the very first slide, guys, when I talked about the spectrum could go from 100% adsorbed to 100% free gas, which means if we have, let's say, 80% free gas, then 20% adsorbed. So we have to evaluate both. Now, during the retrieval of the whole core, we lose some gases, and that gas we need to evaluate as well. So the first one, free gas, or the one at left in here, is evaluated on site, while the adsorbed gas basically is evaluated in the lab. So we start the process actually on site, and then it continues in the lab. And when the amount of free gas desorbed from the shale becomes less and less, then the core actually is crushed as per ASTM methods, and the liberated gas volume is measured, okay? So, and this is done again, the core can be used for other purposes, not necessarily for evaluation of gas volume, and gas composition again can be evaluated right away. We need to know the lithology of our bed, okay? And rock properties have to be actually evaluated. Geomechanics have to be carried out, geochemistry, and formation damage assessment, and all other studies that can be done actually for conventional can be carried out. As I mentioned, the process has to start right away, so there should be a truck supplied with equipment, gas canisters, and a device or apparatus to measure the desorbed gas volume, and then the process continues in the lab. So graphically in here, we should get actually gas content, okay, in standard cubic feet per ton versus square time, okay, elapsed time in here. And what we get a non-linear actually curve, which is exponential increase curve, where at the very beginning of the curve, we lose some gases, and starting from this time in here, so what we have the measured free gas, okay, measured free gas. And then after a long time, okay, as long as the free gas volume is basically decreasing, okay, so we keep monitoring this until it becomes constant, no change, and then a decision has to be taken to crush the core or pulverize it, or whatever you call it. As shown in here, the core actually is basically crushed after 1600 hours. Okay, you talk about almost 4 years. Okay, so it's a tedious process. It takes so long time for evaluation purposes. After that, actually, the adsorbed gas is evaluated. And that's what you see in this equation in here. The total gas is nothing but the lost gas plus canister gas volume plus the residual gas volume after crushing the core. Or it can be put actually in other terms, free gas volume, which is the canister plus lost gas plus the dissolved gas volume, okay? And we know in here we don't talk about conventional reservoir, which means the dissolved gas is 0 or negligible, okay? And the last term in here is adsorbed gas, which is basically measured after crushing the core. So we evaluate total gas as G shale total, and this is we're gonna use later actually to evaluate gas in place, okay? Or in this equation, we use actually GS total that was determined based on experimental measurement. And of course, we plug it into this equation if we know the acreage thickness and we know the bulk density of the gas. This is up there in here. This is used for conventional reservoir, which is the volumetric method, okay, to find the volume. Sometimes can be used actually as a benchmark or to check. The other equation used to calculate the gas content is based in Langmuir equations, which is GC based in Langmuir volume and Langmuir pressure and the pressure in the reservoir. So in terms of curves, Langmuir curve is gas content versus pore pressure. And this is what we have, the blue, dark blue line, okay? When the gas content becomes constant at basically increased pressure, we can find Langmuir volume, okay, BL, and Langmuir pressure PL is determined at 50% of Langmuir volume, okay? At 50%, we can find actually PL. And now if we go back in here, we can calculate quite easy gas content as a function of pressure. So this is the way to calculate the gas in place. Now, during evaluation, we have to get different relations between different properties, okay? There are many properties to measure. In here, we have just two, like methane storage versus TOC, okay? And you could see a linear behavior. And if we get it for one exploration well, this equation or a trend line actually can be used to get estimate for nearby, let's say, wells or exploration wells in the future. Matrix permeability versus porosity, okay, actually can be calculated again and fitted. Trend line again can be used for different production development purposes in the future. As I mentioned, gas content or free gas amount is expected actually to go down as a function of time. If you look at this one, this is collection point in hours or time in hours, okay? And what happens? Actually, after 3.2 hours, if you look at methane actually portion is the largest to desorb, okay? 80% or 80.24% desorbs during the first 4 hours. Then other gases, basically, they follow. If you look at, let me go back. If you look at carbon dioxide, okay? Carbon dioxide is heavy compared to methane, and it takes so long time actually to desorb. So if you look here, so almost 1,100 hours for large amount of carbon dioxide to desorb or to become free. What does this mean? This means that we have to retrieve our core as soon as possible and as fast as possible, okay? So if you look at this comparison in this slide, it makes a comparison between conventional way of retrieving a core and wireline retrieval, fast retrieval. Now, whatever you see in the bar charts in here in red is the amount of lost gas. So in conventional retrieval, the amount of lost gas, okay, actually is so large compared to wireline retrieval. And where we have measured gas actually is less in here, okay? And the residual gas is basically large, okay? So which means to minimize the lost gas, we have to use wireline retriever. And again, this adds cost when it comes to cost of the core retrieval. The other thing is related to evaluation or surface evaluation, okay? It helps a lot actually in terms of knowing the composition of our gas, okay? We need to know whether we are far away from the shale play or not. One way to do that is to plot different ratios like wetness ratio versus balance ratio, as shown at left in here. So basically, wetness ratio is the ratio between summation of C2 to C5 by C1 to C5 multiplied by 100, and the balance ratio C1 and C2 divided by C3 to C5. Now, these are measured using GC, gas chromatography at the surface from the return, basically mud, okay? So the sample is collected from the mud, and this provides almost real-time analysis and continuous analysis. And when we get a gas show based on the analysis, we calculate these ratios directly. And as a matter of fact, this is done for a reservoir in Venezuela, as shown here. And these two ratios, they cross over when we approach actually the reservoir, and the crossover occurs almost 30 to 40 feet above the shale plate. This is actually a good indicator for us to know where to seat our casing, okay, in the top of basically the play. And the other thing, if we want to drill under balance, this is a good indicator to be ready to lighten our mud or to optimize our mud weight and to continue the process of drilling. Then these two ratios separate, okay, and the separation actually occurs significantly, separates significantly or suddenly or sharply when we enter the reservoir. Again, these ratios, or let's say gas chromatographic ratios, give us other indication about whether we hit a drier zone, okay, or dry gas zone, or wetter zone if we plot C2 over C3 versus C1 over C3. So basically, we start collecting data on the surface while we drill. The other thing is needed later to integrate different data sets, okay, between measured using logs and measured actually properties in the lab, okay. This is for quality assurance purposes. So the data sets have to come from different locations, unnecessarily from the bottom hole or from the reservoir. So basically, we need to measure while we drill. So the process starts while drilling. So logging has to take place, and of course, integration of surface measurement with the reservoir measurement will result eventually in a better quality assurance of our reservoir. The other thing in here, number of stages can be integrated along with the GC tracer measurement. As shown in this figure, GC tracer shows actually large or different gas amount, okay, as we move horizontally, and the gas contents eventually is large in some areas, let's say here, last stage, and then in some stages the gas content, okay, is less. The good thing about this one is this is dictated again by having GC tracer available during first vertical exploration well. So basically it gives us better indication about gas concentration, where we have more gas concentrated in the reservoir, and we see this one at the bottom. And this again provides basically drillers with a decision where to place the lateral part of the well, okay, at the bottom of the reservoir. Again, plotting cross ratios, as you can see guys here. So we get some gas above actually, or indication of having gas above the bed. And this is because of the drilling and this ratio. So gas basically goes up ahead of hitting the reservoir. Another thing which is needed, okay, for eventually stages, number of stages, and again, number of stages require go, no go scenarios based on DC tracer measurement and based on elemental analysis carried out based on logging to find the sweet spots, okay? And these two measurements could be integrated to decide where the stage has to be placed in the horizontal lateral part of the well. When it comes to production, we need to know which frac or where the production comes from. So, and this can be studied or investigated using microseismic, okay, mapping. So the fracs could be mapped using microseismic, and as shown in this figure, it was determined out that 3 are most promising fracs among the 8, while the other 3 in here are less promising, and the 2 fracs basically at the edge, okay, or at the heel and toe. So basically they are less promising or poor producing fracs, okay. So again, this is costly process, and it seems it is needed. Well, again, we go back to other issue, which is related to water. Okay, we know that we need large amount of waters, as we're gonna see later on. But now water production or water existence or water use, okay, is good or bad. And they make some problems to us, okay, in terms of cleaning. We have to clean our reservoir. Many well tests actually are affected by water content in the reservoir, and we have to remove that water or to get rid of that water as fast as possible. So where the water comes from, now if we find out we have a continuous flow of water, this is not a good indication while cleaning, I mean, which means basically we have hydraulic fracture growth, and basically if it is a shallow reservoir, okay, not that deep, this frac could grow and reach aquifers, okay? And this will result in basically gravity override and water continuous existence in the reservoir. Otherwise, water is from frac jobs, okay, or contained in some fracs that existed already in the reservoir. So in these 2 cases, we have to clean the water, or we have to pump it up, and different scenarios of artificial lifts can be used, or the velocity dead string actually is a good technique to be used in here, where the velocity dead string is nothing but is a thin pipe, okay, is connected to a production tubing, okay, and then we have a crossover where the gas is injected. Actually, we inject gas from the surface, and then the gas goes through basically the crossover and goes through the pipe, which has very small diameter, and this results in larger momentum and displacement pressure, and it goes back actually through the annulus, okay, and through the crossover goes into the production pipe tubing, okay. So now this process needs actually an addition of surfactants, to create some soap and to change the viscosity of water in here, or to lighten the fluid and make it easier to push or to pump to the surface. Sometimes liquid hold up create actually a resistance to this one and or to this technique, and in this case we have to go for artificial method and to find which one is the best to use. The last part of my presentation is related to environmental issues, and you all know that environmentalists made a big fuss actually of hydrofracking because of different reasons, okay, and different claims are there, different shale gas myths are talking about nowadays. The first, we have almost nine of those, okay, I summarized 9. So the first one is related to land use footprint, okay. It uses actually large area because of frac jobs, and maybe the trucks or machines could go up to 100, their movement and roads, whatever, and of course emission, etc. Volume of water usage, amount of water or volume of water required for frac job. Water quality contamination, we will look at this one. How to manage wastewater, it's not well managed, okay, by let's say drilling companies. Frac water has some chemicals, this is another claim actually and a topic. Air emission, okay, air emission during fracking, actually it was found out in some villages and towns there is a leak of methane, okay, this is another issue, but this is not related to frac. Fracking causes earthquakes, okay, this is another actually claim or myth. Regulation, okay, there are no regulations in some countries, and best practices actually have to be followed. Now, when it comes to water, it's true that almost 4 million actually gallons of water are needed for a single frac job, okay? Now, where to get this water from is an issue, okay? And the other issue, actually 5 to 35% of this volume returns to surface, okay? And returns to surface with completely different quality of the injected water. What should we do with this one, or how this water should be handled and disposed? Different ways actually are practiced by surface companies, or let's say drilling and completion companies. They treat the flowback, okay, and they dispose it into designed wells or abandoned wells. Municipality actually treatment plants are not prepared to accept this water because of the chemical contents as they claim, okay. Sometimes this water is diluted with fresh water and again used for refracking. Sometimes the salt solids and suspended solids are moved, and again the water is used. So treatment is done by some companies, but some do violate, okay, the process. So if this is a valid eventually a claim, then those who raise this claim have to compare the amount of water needed by different sectors of industry, okay? If you look at the amount of water needed, for example, for Marcellus frac job, okay, compared to let's say power plant generation. If you look at the nuclear, in the nuclear industry, they need large amount of water actually for cooling processes. So this one is minimal actually. This amount of water is compared to the one at left in here, or power plant generation water requirement is very marginal. Now, when it comes to chemicals, okay, or how much chemicals we have in the process, okay, actually the frac fluid consists of 99.51% water and sand, okay? So, and the remaining, which is 0.5% chemicals, okay? And in this table, you could see these chemicals and what they are used for. So starting from surfactants, okay, and where is it used? Where do we use these surfactants? We use them in soap, we use them in deodorant. So basically, most of these chemicals are used in our daily life, okay? So they are not harmful, okay? So acids, they said acid actually one of the most harmful or hazardous. We use them in our swimming pools as well. So eventually, and this amount is small, okay? And most of those chemicals, eventually they interact and their property does change as the process goes on. So the problem with this claim, so in here we have two claims, water quality issue contamination and chemical used in frac fluid, okay? So there is no evidence whatsoever, okay, I tried just to download a paper that shows groundwater aquifers were polluted by frac fluid, okay? There is no evidence at all. There are some scientists at Duke universities who carried out some studies related to this. And what they found actually, they found only traces of methane. Nothing else actually, or none of those chemicals were found in their wells that exist basically where they live, okay? And nowadays, up to my knowledge in the States, there are new legislations with respect to water analysis. If you live in the vicinity of a well, let's say up to 2,500 feet, the owner of the well or operating companies, they have to make regular analysis for the quality of the water you use at home. And in case if there is a pollution, some other measures have to be taken, whatever. I don't know what is it exactly, but this is the legislation. Now, when it comes to earthquake, eventually the fracking is done in a small portion of the reservoir, okay? And it does not propagate so high, usually done versus vertical stress. Some companies, I believe Hamid and Geomechanics guys can address this better than me, but based on the figure I took from Talisman Energy in here, you see a comparison in terms of Richter scale between an earthquake in southern Quebec in 73, where it is in the range of, let's say, 1 to 4, okay, degrees Richter, and a hydrofrac job carried out 2 kilometers deep, okay, in a shale gas, which was determined with negative value, negative impact actually, okay, or negative Richter, -4 to -3, which means this frac is 10,000 times smaller than this basically earthquake. When you talk about 4 Richters, okay, we don't feel it. It's just a small shake and no one can feel it. Now, with respect to emission, if we compare it to coal, actually shale gas is environmental friendly gas, and you look at whatever in the bar charts in here in blue, okay, and you see that coal eventually produces more carbon dioxide than methane, and less methane than eventually the shale gas or methane shale gas, okay? Okay, so in summary, guys, the go, no-go scenario with respect to shale gas is so difficult to take. So it entails lots of work, it entails lots of estimations, okay? And again, this spans the life cycle of the well. This could be approached differently by different surface companies and of course operating companies. Shale gas projects are a project that requires a high cost, okay, when it comes to assessment and analysis. USA shale basins can be used as a good benchmark, Nevertheless, there are no two rocks that are exactly the same. So shale gas in the state is completely different from, let's say, the one we have in Saudi Arabia or in Algeria or in China. So lots of investment is required for this type of reservoir. And of course, if gas prices will go up, okay, this could be a good driving force for some countries who don't produce fossil fuels, okay? But if the gas prices will be low and oil prices will be low, so targeting such a play might be undesirable. So I'll stop it here. I took actually more than what I have to take. I'll stop it here. If you have any question, please go ahead and ask.
Thank you very much, Dr. Aziz. It was a very nice presentation and a very structured way to actually looking at shale gas development. I personally learned a lot about from it, and I hope others also got the same feeling. So since it's evening in Cairo, I believe you are available to take some questions, unless you want to go right to the bed, right?
No, it's okay.
Okay,
I'm with you.
So if anybody has a question, I invite you to raise your hand so I can open your microphone and you can directly ask your question from Aziz. Or is it still possible to post your question in the chat section if you don't want to talk for any reason?
You can provide my email, Hamid, in case if.
Sure.
Or your email. Your email.
You didn't put it on your slide somewhere?
Yes. Yeah, you can.
Okay. Yeah. Let's check again. So it seems that people don't have question.
Okay.
As I said, your presentation was quite clear and very well structured, so easy to understand.
It's my pleasure. And thank you so much, Hamid, for having me again. And hopefully we will meet one day.
Thank you very much. And please feel free to share your PDF version if you are willing to share with others. Otherwise, there's no push. And I greatly appreciate your participation in our program. And thank you to everybody else who attended the presentation. Our next presentation is next next Monday, sorry, and is going to be on geothermal. So just follow us on LinkedIn to get the most updated information about it. Thank you very much and have a great day or night.
Thank you. Bye-bye.